In this video, we are going to apply our knowledge of Gauss's theorem in determining electric fields due to symmetric distributions of charge. Now, with symmetric distributions of charge, life becomes very easy when we are calculating electric fields using Gauss's theorem, and the use of symmetry helps in easing out use of symmetry, and Gauss's theorem helps in easing out the calculation of electric field intensity. Now, in calculating electric field intensity using Gauss's theorem, what we really need to do is we need to consider a surface, a closed surface, because Gauss's theorem is applicable on closed surfaces. So we need to apply Gauss's theorem on closed surfaces, and the surface that we choose should be such that over the surface electric field should be either tangential or constant and normal to the surface at all locations of the surface. Now, why so? Well, because when we apply Gauss's theorem and we are calculating flux, calculation of flux becomes very easy if the field is tangential to a surface. Now, this is something I have discussed in the previous video as well, and we are discussing it again here. That if the field is tangential to a surface, let's say this is the electric field and it is tangential to the surface of this board, then the flux through the board will be zero, because no lines of force pierce through the surface. And if the electric field is normal to the surface and constant in magnitude at all points, then the flux is simply the magnitude of the electric field multiplied by the surface area, and we have a very easy calculation for flux. Now, when the calculation of flux is easier, the calculation of electric field also becomes simple, and this is what we are going to learn, the simple calculation of electric field using Gauss's theorem. That's the topic of discussion today. Now, let's take up an example of electric field calculation for a charge distribution that we are already familiar with, so that we know that this gives us the right kind of results. So let's start with an infinite line of charge. Now, you will definitely recall that with line of charge we had to use integration and calculate a summation of electric fields due to charge elements. Now, with an infinite line of charge, using Gauss's theorem, we'll be able to arrive at the magnitude of electric field quite easily without the use of integration. Now, let's have a look. This here is a very long, infinitely long line of charge. It has a linear charge density lambda. Lambda is the linear charge density. Now, we are interested in the calculation of electric field at some distance from it. Let's say that distance is r. Now, the symmetry of this charge distribution tells us something. If we consider two symmetrically located elements, one over here and one over here, symmetrically located with respect to this point. So this distance and this distance are equal, the elements are equal. Then the field due to this element, will be in this direction. The field due to this element will be in this direction. Both are equal fields and both are symmetric, so the angles are all same here. Now the result of this is that the components of these electric fields which are parallel to the line of charge, these field elements which are parallel to the line of charge, they will cancel out. And the field components which are perpendicular to the line of charge will add up, giving this resultant electric field. So the resultant electric field here can be easily determined in terms of direction, that is not the magnitude. We've determined the direction of this electric field as being perpendicular to this line of charge here. Now the next step is to calculate the magnitude of this electric field, and here we'll be using Gauss's theorem. Now we have to come up with a surface over which this electric field is either normal and constant in magnitude at all points, or it is tangential to the surface. Now one such simple surface would be a cylinder for which the line of charge here is the axis. So this is a cylinder we have imagined, cylindrical surface. Let's say the length of this cylindrical surface is L, and this axis here is the axis of symmetry. Also this line of charge is coinciding with that axis of symmetry. So we've got a cylindrical surface. This line of charge is the axis of that cylinder, or the axis of symmetry of the cylinder, and for this cylindrical surface, of course it has a radius r, its length is L. For this cylindrical surface, the electric field on the curved surface will be normal to the surface at all locations of the surface. Also, if you look at the flat surfaces, the electric field will be tangential to the surface. So for the flat surfaces, the electric field is tangential to the surface, and for the curved surfaces, the electric field is normal to the surface. Since the electric field is tangential to the surface on the flat surfaces, the total flux on the flat surfaces will be 0. The flux on the flat surfaces is 0 because the electric field remains tangential to the surface, and this has come up in our discussions earlier about electric flux, that if the field is tangential to the surface, the flux on that surface is 0. So for the flat surfaces, the flux is 0. On the curved surface, the electric field is normal to the surface at all locations and has a constant magnitude, because all the points on the curved surface are at the same distance r from the line of charge. So the flux on the curved surface will be the magnitude of the electric field. We are calculating the flux now on curved surface. Now this flux equals the magnitude of the electric field times the curved surface area. Now how much is the curved surface area? It will be 2 pi r times L. That's the flux on the curved surface area. Now this flux of the curved surface area is in fact the total flux for this closed surface, this cylinder. Remember, the cylinder is made up of two kinds of surfaces, the curved surface and the two flat surfaces on the top and at the bottom. So they all complete one closed surface. For this closed surface, we have the flux here. Now, once we have the flux, let's apply Gauss's theorem. This total flux now has to be the enclosed charge by epsilon naught. Now, how much is the enclosed charge here? The length of this line of charge, which is enclosed inside the cylinder, will be equal to the length of the cylinder. The length of this line of charge that is enclosed inside this cylinder is actually this length here. The part of the line of charge that I have enclosed in this black rectangle, this length will have to be, of course, L. And when the length of this enclosed portion is L, the charge on it will have to be lambda times L, because the charge per unit length on it is lambda. So charge on the length L will be lambda L. This L cancels on both sides and we get the electric field now as lambda divided by 2 pi epsilon naught r, which, if you recall, is the correct magnitude of the electric field due to a line of charge. This is something we have derived earlier. So no integration required, no summation required. Very, very simple calculation. We did not even have to calculate the electric fields due to individual elements, and of course there was no need for summation as well. So this is a very, very simple method for calculating electric fields. Now, a couple more calculations of this nature. The next we are discussing is an infinite sheet of charge. Now, with an infinite sheet of charge, again we are aware of the electric field. If the surface charge density is sigma, then the electric field is normal to the sheet of charge and has a magnitude sigma by 2 epsilon naught. So let's consider this to be the cross section of an infinitely large sheet of charge, or maybe I can try drawing a more three-dimensional figure so that things become a little more clear. So we have a very, very large sheet of charge here. This is the sheet of charge. This sheet is large, so what we'll be doing is we'll be treating it as infinitely large in our calculations. Now, because of the symmetry, if you consider an element here and an element here, the electric field at a point at a small distance from the sheet will be directed perpendicular to the sheet, and if sigma is positive, it will be outward from the sheet. If the charge density sigma is negative, it will be towards the sheet. Now, we have to think of an appropriate Gaussian surface. The Gaussian surface that we're going to consider here is a cylindrical one, but this time the cylindrical Gaussian surface that I'm drawing has a horizontal axis like this. This is the curved surface, you have the flat surface here. Now, this part of the cylindrical Gaussian surface that I have drawn is to the right side of this sheet of charge. There will be a part of this Gaussian cylinder, Gaussian surface, which will be behind this sheet of charge to the left of it. That part I'm drawing as a dotted drawing. This is the part which is behind this sheet of charge. Now, there is a part of the sheet that is enclosed inside this cylinder over here. This part. This is the part of the sheet. This green shading represents the part of this sheet of charge that is enclosed inside our Gaussian surface. Now, the electric field is directed normally, that is perpendicular to the sheet of charge over here, as well as over here on the other flat surface. The cylinder has two flat surfaces, one here and one here. The electric field here as well will be this way. On the curved surface, the electric field will be tangential, and therefore we are spared the agony of calculating flux on the curved surface. On the curved surface, the flux will end up being 0. Let's say the cross-sectional area of this Gaussian surface is A. The cross-sectional area of this Gaussian surface, the cylindrical Gaussian surface, has a cross-sectional area A. The electric fields on both sides are E each. Let's say the length is 2L, L on either side. Now, we'll actually be calculating the electric field at a distance L from the sheet, right? Now, if you look at the flat surfaces, the field on the flat surfaces will be normal to the surface and will have a constant magnitude throughout. So on this flat surface here, the flux will be E times the area A. The flux on this surface will also be E times A, and the flux will be positive on both surfaces because the electric field lines are coming outward from the surface. If you recall the previous video, we have already discussed that when electric field lines leave a surface, their flux is positive. So the flux is positive on both the flat surfaces. On the curved surface, the flux is 0, and this therefore gives us the total flux through this Gaussian cylinder. Now this total flux will be equal to enclosed charge divided by epsilon naught. Now the total charge on this sheet here, not the sheet, I mean the total charge enclosed inside this Gaussian surface will be the charge on this shaded green portion of this sheet. Now this portion also will have an area A which is equal to the cross-sectional area of this cylinder, and therefore the charge on it will be the charge per unit area times the area A. This is the charge enclosed inside this Gaussian surface. Now the area A cancels out and we have 2E here. This equals sigma by epsilon naught, and the field E now equals sigma by 2 epsilon naught, which you will recall is the correct value, the correct magnitude of the electric field due to this sheet of charge. So the calculation of electric field becomes so much easier provided we have symmetry in the charge distribution. Now we'll be taking up a couple of new cases of calculation of electric field, two cases that we have not discussed so far. These are the cases of spherical charge distributions. Now to start with we'll be talking about a uniform spherical shell of charge. We're talking about a uniform spherical shell of charge. Now, what do we mean by a shell or a shell of charge? A shell is something that is entirely there on the surface. It's hollow on the inside. So a spherical shell would be something like a table tennis ball. If you've seen a table tennis ball or even a tennis ball, it's a shell. It has small thickness. The entire mass or the material of this body is on the surface. The inside is completely hollow. So such a body would be called a shell, and as this suggests, it's spherical in shape and it has a uniform distribution of charge on the surface. So we have here a uniform spherical shell of charge. It carries a uniformly distributed charge Q over it and has a radius capital R. This charge Q is distributed entirely on the surface. So we are now interested in calculating the electric field due to this shell of charge. Now, using symmetry, we can determine the direction. Now, have a look here. We consider this little element and we are looking at a point which is distant small r from the center. Let's say this point here. This is where we are trying to determine the direction of the electric field. Now, the electric field due to this element at this point will be somewhat like this. Now, consider a symmetrically located element here. Its electric field will be directed this way. Now, quite easy to see that the components of these electric fields which are perpendicular to R, that is along this direction, the components of these fields along this direction will cancel out, being equal and opposite. The components of electric field in this direction will add up and we have an electric field which is in the radial direction. Now, this is a conclusion that we will keep in our mind for all kinds of spherical charge distributions. We are going to make an assumption that the electric field is radial. For all spherically symmetric charge distributions, electric field will always be radial. Now we have to develop a Gaussian surface for which we calculate flux and then calculate eventually the magnitude of this electric field. So to start with, we are calculating electric field at a point inside this shell. So we are looking at the interior of the shell. We are looking at inside the shell. So inside the shell, this distance small r from the center will have to be less than the radius capital R of the shell. Now, the Gaussian surface we draw should have such a shape that the electric field is normal to it and constant in magnitude throughout. What I do is I draw a spherical shaped Gaussian surface here. So this is a spherical Gaussian surface which is concentric with the shell. Concentric meaning it has the same center. So I've drawn a concentric spherical surface as my Gaussian surface. Electric field will be normal to it at all locations and will also have the same magnitude because all points are at the same distance from the center and therefore enjoy the same kind of position everywhere. and therefore the electric field will be normal to this surface at all points. Also will have a constant magnitude at all points. So if the electric field is E here, it is E here as well in magnitude, and is perpendicular or normal to the surface. Now, calculating flux over the surface becomes pretty easy. Electric field times the surface area. Surface area is 2 pi r square, and this flux equals the enclosed charge divided by epsilon naught. So the charge enclosed inside this Gaussian surface is essentially 0. Why enclosed charge is 0? Because all the charge is outside this Gaussian surface. The entire charge of this shell is there on this surface here, the green surface. There is no charge at any point inside this green surface. So the charge inside our Gaussian surface happens to be 0, and so is the field. So this is what we call the shell theorem. It's part of what we call the shell theorem, the one that you studied in gravitation as well, that the electric field, or even in case of gravitation, the gravitational field inside a uniform spherical shell is 0. Now moving outside the shell, let's consider a point here at a distance r. So this time we are moving outside the shell. Small r is greater than capital R. So we are now in the exterior of the shell. We are outside the shell now. So small r now is larger than capital R. Again, what we will be doing is we will draw a spherical Gaussian surface, and knowing the symmetry of this arrangement, we know that the electric field will be radial and therefore normal to the surface at all locations of the surface. So it's fairly similar. The calculation of flux on this surface will be completely similar, absolutely identical in fact, to the electric flux calculation for this Gaussian surface. So for this outer Gaussian surface, the flux is E times 4 pi r square. In fact, it should have been 4 pi r square here as well. Here it didn't matter because it was going to be 0. 4 pi r square, that's the surface area of a sphere. E times the surface area of this sphere, that's the total flux, equals the enclosed charge by epsilon naught. Now the entire charge of the shell is enclosed inside, and therefore we have Q by epsilon naught. The electric field therefore is Q divided by 4 pi epsilon naught r square. Now, which is pretty interesting. This is the expression for electric field of a point charge placed over here. So what we've seen is that if we have a uniform spherical shell of charge, this green thing, at any point inside it the electric field is 0, and for points outside it, it seems to behave like a point charge placed at the geometric center. So in the interior the field is 0, and if you go outside the field is Q by 4 pi epsilon naught r square. I'm giving you another alternate expression. If the surface charge density is given as sigma, then you can express sigma as Q divided by 4 pi capital R square. So if you multiply and divide by capital R square over here in this result, E equals Q by 4 pi epsilon naught R square, multiply and divide by capital R square, and you can see sigma over here, and in terms of sigma, therefore this result will be sigma times capital R square by epsilon naught into small r square. So the same result can be expressed this way as well. Which concludes our discussion on spherical shells. The next discussion we are having will be on a solid sphere of charge. Now with a solid sphere of charge, the change that happens is that charge will now be distributed in the entire volume and not just on the surface. So if that's the aspect in which solid sphere is different from a spherical shell. Now let's consider a solid sphere of charge. Let's say this is a solid sphere of charge, and I'm shading it to indicate the fact that charge is now there in its entire volume, not just on the surface. So it has charge distributed all over its volume. The radius of this sphere is r, and the charge inside it is q. It is uniformly distributed in the volume, and we can now define also its volume charge density, volume charge density. This volume charge density rho would of course be equal to Q divided by the entire volume, which would be 4 by 3 pi r cube. So we might end up making some use of this a little bit later. Now remember, this is also a spherical distribution of charge, spherically symmetric distribution of charge, and therefore at any location the electric field will have to be directed radially. So now let's first look for the electric field in its interior, inside it. That's small r being small r, the distance from the center, being less than capital R. So we are determining the electric field at this location here. Again, since the field is symmetric, radially directed everywhere, we draw a spherical Gaussian surface just like we did in case of a spherical shell. So this is our Gaussian surface, and the electric field is directed normally at all points, must have the same magnitude because all points have the same distance from the center, all points are identical, and therefore the field is same everywhere. Now applying Gauss's theorem, E times 4 pi r square, that's the flux. This flux equals the enclosed charge by epsilon naught. Now what's the enclosed charge inside it? That will be rho times the volume enclosed inside this Gaussian surface. The volume here is 4 by 3 pi r cube, and after making some cancellations here and there, we get electric field equals rho by 3 epsilon naught times r. And since the electric field and r are both radial, we can use vector signs here. Now if rho is positive, electric field is in the same direction as r, and if rho is negative, electric field is directed opposite to r. So for positive charge, field is radially outward. For negative charge, field is radially inward. So as usual, we are discussing electric field directions assuming positive charges. In case the charge is negative, the field simply reverses in direction. So this is the field inside a solid sphere. What we can also do now is replace this rho by this result, and the magnitude of the electric field now comes out to be Q by 4 pi epsilon naught r cube times small r, and E and R can have vector signs on them. What we've done here is simply replaced rho from here. So the 3 cancels out and you end up with this result. That's the electric field inside a uniform solid sphere. Now the moment we move outside, things change. Now for this location, if you are interested in calculating the electric field, again it will be radial. We'll need a Gaussian surface, which will again have to be a spherical one, so that the electric field remains normally directed everywhere. So this is my spherical Gaussian surface here. For this spherical Gaussian surface, which is completely outside the solid sphere, so we are now in the exterior, that is, small r is now greater than capital R. Flux calculation, E times 4 pi r square, this equals 1 by epsilon naught times the enclosed charge. But the interesting thing now is that the entire charge Q of the sphere is enclosed inside. Therefore, E equals Q by 4 pi epsilon naught r square. So even with a solid sphere of charge, uniform solid sphere of charge, we find that the electric field is exactly like that of a point charge placed at the center. So this behaves, even a solid sphere behaves like a point charge placed at the center. So whether a spherical charge is a solid one or a shell, for points outside it, it behaves like a point charge placed at the center, whereas in the interior the behavior is different. Inside it, a shell produces zero field, whereas a solid sphere does produce a field, which incidentally is directly proportional to the distance from the center. And if you are to draw a graph showing the variation of magnitude of electric field with the distance from the center, then the graph will look like this. In the interior, there is a direct proportionality with r, so we have a straight line. And in the exterior, it's inversely proportional to r square. So we have a graph that looks like this. At large distances, this field will become practically zero. This point here, of course, is small r equal to capital R. So in this video today, we have discussed electric fields due to a few different charge distributions. The couple that we had knowledge of even before this video, but we've added to our knowledge in the sense we have now discussed about spherical charge distributions as well. This knowledge is very, very critical. The spherical charge distributions are kind of very, very important in nature. Also, why spherical charges are very important is because calculations of fields and other related quantities for spherical charge distributions, these calculations are easy and possible, and therefore any physics exam will prioritize questions on spherical charge distributions, and therefore it's kind of an important concept, very critically important concept, considering exams as your focus. So with this we conclude this video. In the upcoming videos we will be applying Gauss's theorem and the knowledge we have acquired today in doing some problem solving. So the next video will be about problem solving related with these charge distributions, also otherwise using Gauss's theorem. So thanks very much for watching. We meet again and then we discuss electric fields due to various charge distributions, which can now be broken up into the kind of charge distributions we've studied today. Thank you very much for watching.